Yes, it's on by purpose. Yeah. Yeah. Okay. You sure? Sorry? So, okay, so today I will discuss, I will show you um, a very slow, almost frozen dynamics that is observed in this discrete nonlinear Schrödinger equation, and that is related to negative temperature states, but also to ergodicity breaking. So before starting, let me say that this work has been done in collaboration with these people, essentially from Florence and from Scotland. And here is a very brief outlook of my talk. So I will focus on the role of the nonlinearity in determining the equilibrium and out of equilibrium properties of this discrete nonlinear Schrödinger equation. And here is, so basically my talk will be divided into three parts. In the first part, I will show you what are the essential features of this slow process that involves negative temperature states and energy localization. Then in the second part of my talk, I will discuss some results related to stochastic versions of the discrete nonlinear Schrödinger equation that helped us to understand, in some sense, the basic rules of the game. And then in the last part, I will discuss purely dynamical effects. Okay, so let us start. This is the model. Again, this is a one-dimensional discrete nonlinear Schrödinger equation. For your convenience, I say that, I repeat that these Z, N are complex variables. And as you see, the structure of this equation is you have a nonlinear local term plus a linear nearest neighbor coupling. This model has many applications in physics. The most important ones are in nonlinear optics, as this equation describes the evolution of light inside a system, arrays of nonlinear coupled waveguides. And another important application is in cold atom physics, as this equation is related to the Gross-Pitaevsky equation, and it describes the evolution of Bose-Einstein condensates inside optical lattices. Okay, so let us discuss this point. So I already shown this slide, and for what concerns the thermodynamical, yeah. You can eliminate this part. You perform a transformation of variables, and basically it's equivalent. Yeah, yeah, yeah. That's an important point. Yeah, and let me also remind you that this model is non-integrable. So basically, it displays chaos, and this will be an important ingredient for what will follow. So you have two conserved quantities, the total Hamiltonian and the total number of particles, that is basically the total norm of the wave function. And the thermodynamics is summarized here in this diagram, where you plot the average energy density versus the average mass density. Okay? So again, one point here is an equilibrium point. It can be characterized by a temperature and a chemical potential. You need two parameters because you have two independent conserved quantities. And we already discussed that here you have a positive temperature region where you have standard Gibbs measure, and you have negative temperature states. Of course, as I already discussed, in principle, you can play with the symmetry that allows you to reverse the sign of the Hamiltonian. This will allow you to flip this plot with respect to the horizontal direction, But this is not, does not, you can decide whatever, what is your convention. This will produce a reversed convention for temperature, but it does not matter, okay? So let's take this picture, and let us see what happens if I take a point here and I evolve the system. Before showing this, let me show the microcanonical definition of temperature in its the full definition. So basically, here is the full structure, and so as you see, it's quite complicated, but you realize that it's actually a function of derivatives of the energy, the total energy, and the total number of particles. So if you want to put this definition in a computer to measure temperature, you have to be quite smart, because otherwise it can happen that your computer takes more time in computing this temperature than for evolving the system. But this also allows me to answer Elie Barkay's question that was about the inversion of energy. So the question was, what happens if I change the signs of H? Where do I see that the temperature changes sign? And here you can see, basically, let us look at this expression. So here you have this quantity that is basically a norm of something. So this is always positive, so we do not care about. So I'm looking for odd quantities in the energy. So this, of course, is an odd quantity, this gradient, and this E0, what is its definition? So it depends on this N0 that again is a gradient of H. So this E0 is odd in the energy, but again this scalar product is even. So I have to go inside this square bracket, and I see again this E0. So please notice that E1 does not play any role because it does not depend on the energy. And so you realize that indeed this observable is odd. Okay? So even I didn't. So what are the? I didn't understand. No. Density of. Basically, here this diagram comes from Gibbs measure. Yes, yeah. Yeah, well, I mean, they're always I mean, no, numerically they correspond. So you can't. No. If you perform a simulation, so suppose you take a point here, it corresponds to some temperature. Then you perform a simulation. You measure this temperature by means of this expression, and you get the same temperature. So, okay. So at least numerically, so maybe you can. Okay, so here is a typical negative temperature state in the DNLS equation. So here I'm showing you some amplitude profiles. Here is space, and you see they have this property. So you have basically a flat background, that is this small one, on top of which are superposed some high amplitude objects. So these objects actually are very well-defined states that are called discrete readers. So if you want to know more about discrete readers, here there is a review by Sergei. But let us recall their main properties. So they are these discrete readers are exponentially localized in real space, okay? And then they display an internal frequency, omega, that does not belong to the linear spectrum. So they are intrinsically nonlinear, okay? They are solutions that are pretty generic in nonlinear discrete models, and they are the consequence of nonlinearity of the system. There is no role of the disorder. Here I'm talking about ordered system, okay? Then you have a sort of zoology. You can find static breeders, moving breeders, and so on. And an important property is that they are stable solution. And due to their stability, basically, they allow also for experimental observations. Okay. Here we come to a very quite subtle point, because there were some paper by Ben Rumpf on this discrete nonlinear Schrödinger equation that proved that if you consider on the basis of entropic arguments, basically this typical state that you obtain, for instance, with simulation, does not correspond to the equilibrium state, the true equilibrium state. Indeed, the true equilibrium state is completely different. It is composed by only one giant breeder that somehow collects the excess energy that was previously stored here, superposed to an infinite temperature background. Okay? So this is quite important, because you see that if you do not consider the site where the breeder is, basically all the rest of the chain is infinite temperature. So from this point of view, there is no room for negative temperature. This is the prediction of statistical mechanics. But there is a but, because you may argue that, okay, what is the typical relaxation time to go from here to here? So it turns out that this time can be astronomically long. So what I'm going to show you is what happens over long, but not astronomically long time scale. And this is what happens. So these are some results that we obtained some years ago. So here, basically, I'm evolving this system microcanonically. I select a point in the negative temperature region. And here in this diagram, I'm basically plotting the evolution of breeders. So here is time that is going vertically. Here is space. And a black point means that this point is higher than a certain threshold. So it's a very simple way to identify breeders. And you see that breeders actually are produced, but they display a sort of stationary behavior where breeders are continually created and destroyed. And indeed, if you perform some statistical analysis, you see that independently of the initial condition that you choose, basically this density of breeders is constant, stays constant. And if you measure the temperature according to the microcanonical definition, you see a negative temperature, not an infinite temperature. The microcanonical temperature. Okay? I see a negative temperature. So this means that in some sense the system is frozen in a sort of metastable state where the temperature is negative. In this dynamic, in this simulation, no. We were not able to see. Okay. And then let me mention also some recent results by the group of Flach, where basically they were able to identify a region where weak ergodicity breaking is found. What is I would say interesting. So here I'm taking their picture. So here the infinite temperature line is this black solid, and here this red dash curve identifies this small region where actually, according to time series analysis, you have an ergodic behavior. Okay, so there is something really non-trivial. So I think probably Carlo will say something more on this, so I leave to him probably this point. And so what is the point? At this stage, one would like to understand what is the physical origin of this metastable state. So it turns out that actually the dynamics is very complicated, and you may imagine there is a sort of competition between entropic effects and dynamical effects. So one would like to decompose this problem in order to understand better the rules. A possible way to do this is to study stochastic models. Okay, so I want to just investigate the role of entropic effect. I just neglect dynamics. How can you do this? Basically, the idea is to consider the discrete nonlinear Schrödinger equation and its constraint, and to define the simplest stochastic model. What we did was to basically neglect this interaction term in the Hamiltonian, and you end up with these two constraints that correspond to a system of non-interacting sites. And then you can now define a stochastic evolution rule according to a microcanonical Monte Carlo algorithm. So what is the point? So the point here, the idea is to select a triplet of states randomly on this chain, and to perform some updates. Okay. So suppose you have 3 states, then you have 2 constraints, then you are left with 1 degree of freedom. And here, so here in this plot, I'm showing the 3 masses of the triplet, and here this red line corresponds to this degree of freedom. So actually, the microcanonical algorithm corresponds to evolve, to pick a random point here, and to perform a random update. Yes, just for 3 sites. In this way, you are sure that you exactly conserve these 2 observable. Okay? Then you repeat, you choose another site, and you perform these updates. Here is, you see the difference. So here is a typical state with almost uniform amplitudes, where it corresponds to this circle here, but it turns out that if you have a sort of breather, so a localized state in this triplet, basically your phase space is separated into 3 arcs. Okay, so at this level there is something already non-trivial. What is interesting is that this model has the same structure for what concerns the phase diagram. I have a positive temperature region, I have a negative temperature region, and what I'm going to do is to pick a point here in the negative temperature region, and again, see what happens. So I'm doing exactly the same within this stochastic model. And what you see is a coarsening of breathers. So here again, I'm plotting the evolution of breathers as a function of time. I start from an initial condition where there are some breathers, and indeed you see here the convergence to the equilibrium state that was described by Rumpf. You see that the number of breathers decreases as a function of time until you are left with only 1 breather. Okay, so the equilibrium state is here, and if you compute the average breather distance as a function of time, you see that this distance increases in time with a subdiffusive exponent that is 1/3. So this is actually correspond to a coarsening dynamics of breathers. Yes? So for the, I think that for this model there is no Gibbs. I mean, yeah. The Gibbs. Oh, wait, it dies. Sorry. Yeah, I will show you. And so this is at this level is this is a known phenomenon. This is correspond to a condensation phenomenon. Here are some references where these condensation phenomena are studied, And the creation of this giant breather basically corresponds to the creation of the condensate. Okay, here is an answer to your question. So basically here is the evolution of when you start from you put a single breather in the Gibbsian regime, and you compute its energy loss. So you see that these energy losses are increased in time with a diffusive law. We are not surprised about diffusion because basically here we are putting diffusion by hand. And okay, this is known. And so basically you can see two different outcomes from this relaxation. Either your breather dies because okay, you are in the Gibbsian regime. Either your background reaches infinite temperature, and then you stop. Okay. Good. In order to understand the origin of this coarsening process, what one can do is now to study the interaction of two breathers on an infinite temperature background. Okay? So this is the setup. I take an infinite temperature background, I put on one breather. If I stop here, this is equilibrium, nothing happens. But I put another breather, such that the breather distance is basically a half of the whole length chain. Suppose you have periodic boundary conditions, and I see what happens. So basically, one of these two breathers has to die. And here, indeed, here I'm plotting the two energy of the breathers as a function of time. You see that they start interacting, even if they are not in direct contact, until one of these two guys dies. If you compute the energy diffusion of one of these two breathers, you see that okay, there is a linear increase in time, but the associated diffusion constant decreases as a function of the length of the total length. So this means that the higher is this breather distance, the smaller is this diffusion constant. And you understand, because basically in order to interact, this breather has to release an excitation here, then this excitation has to diffuse until here, and has to be reabsorbed. So there is this effective interaction that is mediated by the background. By spontaneous. Yes. Yeah. Yeah, just spontaneous sympathy breaking, I would say. There is no. Yes. Yeah. If you repeat many experiments, you will find on average 1/2 and 1/2. Okay. So if you do now some trivial power counting, you see that the typical time that you need to destroy one breather scales as the third power of the system size, and this explains very simply this coarsening exponent. Of course, you can be more precise, you can do some analytical descriptions, but basically this is the story. So in the end, we understood there are two time scales, at least in this simplified stochastic model. There is a fast time scale that is related to direct energy transfer from the breather to the background, and then there is a slow one, or the n2 power 3, that is related to breather energy exchanges mediated by the background. Okay. So this tells you that already for stochastic system there is something non-trivial. There is this subdiffusive exponent, and now let me come back to the original problem, to the discrete nonlinear Schrödinger equation. So what I'm going to show you in this third part is that a very slow breather dynamics appears also in the negative temperature regime. And in particular, I will show you that the breather relaxation timescales are exponentially small with respect to their mass. So here is the setup that I'm going to consider. So here I take a background, a positive temperature. Here I consider the discrete nonlinear Schrödinger equation. And I put one breather. So since I want to be sure that the background stays at positive temperature, I connect this chain with external heat bath that fixes the temperature to positive one. So here is the setup, the imaging. Then I excite one breather here. And what happens is this. So here I call B the mass of the breather. I start from an initial mass, and I follow this mass as a function of time. So this is exactly the same relaxation study that I was performing with the stochastic system. And now you see that by increasing the initial breather mass, you see a dramatic increase of the breather death time. So notice that this is a logarithmic scale. Okay, and if you perform some more refined statistical analysis by averaging over many realizations, you find that there is a rather clean exponential increase of this death time as a function of the initial breather mass. So this means that in the thermodynamical limit, where breathers could be arbitrarily tall, this time could go to infinite. And let me now consider, yes. If you do not consider in that case, so if you take a small system and a huge breather, basically you will enter the negative, the non-Gibbsian. You can imagine, in order to reproduce these experiments within the microcanonical point of view, you need to take a very, very long chain, a very, very long background. Here is a trajectory. So here I'm plotting the masses of 3 sites, basically the site n equals 0 is the breather site where I place initially the breather. So this is the back curve, and then I plot also the 2 neighbors. You see that there is something non-trivial because so here is the mass, it fluctuates for a long time, then it displays a jump, and in some cases, as you see here, the breather can jump from one side to the next one. And you see there is a strong correlation of these jumps with high excitation of the breather of the neighboring sites. And if you enlarge this area, suppose you are here, you see that for a quite short time, basically this breather is delocalized over 2 sides. So as I will show you in a while, this corresponds to a creation of a sort of bound states, where the breather is delocalized. And so you clearly see that the typical relaxation dynamics is composed by 2 stages. You have let's call it a laminar period where basically nothing happens except for very fast fluctuation, and these jumps. So let us analyze in more detail these laminar periods, so periods where you do not have jumps. So, so if you want to, so if one has to start from some point, one possible thing is to compute the mass correlation function. So here is the breather mass correlation function, and what you see is that okay, for very short times you have correlations, but typically for times greater than 1, you lose any memory about the initial condition. And this is the effect of the background. Remember that this background is chaotic, and so one may think that for times longer than this unit time, one could perform some sort of statistical analysis. And the statistical analysis that we performed was a principal component analysis. So what is the idea? So I want to really find, to understand why the breather does not relax. So here I'm considering three sites where the breather is on site 0, and okay, they correspond to 5 real variables, and I compute a correlation function. So it turns out that from this correlation matrix, you have one minimum eigenvalue that is very, very small. So this is the behavior of this eigenvalue as a function of the initial breather mass, and you see that there is a power law decreasing as a function of this B. So this allows you to identify a direction where actually breather, the dynamics is very, let's say, where fluctuations are very, very reduced. Indeed, if you compute the eigenvector, that is this quantity, you find that, so here is a comparison between the breather amplitude, that is this black curve, and the behavior of this quantity. So we call this a quasi-conserved quantities, because it corresponds to this very, very small eigenvalue. And you see that basically the white points correspond to this evolution of Q1, and they display very much reduced fluctuations. So in our opinion, this could correspond to a sort of adiabatic invariant that is preventing breather relaxation. Okay, so at the level of the principal component analysis, you find this constant C, but which is numerical, but you can perform some perturbative calculation, and you find that basically this C is the inverse of the breather frequency. So we found this adiabatic invariant that could explain why breathers do not relax. One could imagine, for instance, to perform a higher order calculation to refine this estimate. So let me go to the other part of the story. So sporadic jumps. So what is the nature of these jumps? As I shown you, that you have the creation of this bound state, and indeed we found that typically this corresponds to the creation of dimer states. So in principle, you can study the dynamics of a breather dimer, and you find that in order to create this bound state, you need background site that is needs to overcome this threshold. And here we performed some analysis where basically we started from a breather and we artificially excited one background site where R is a parameter from 0 to 1. Okay, and we found that the largest energy variation, the largest jumps, indeed are localized for correspond to this dimer threshold. Okay. And so this tells you that again, these sporadic jumps correspond to rare events. Because if you fix, if you imagine to fix your breather mass quite high, you need for your background needs to display a rare giant fluctuation in order to create this bound states. And in the simplest approximation, where you consider the background in equilibrium at the temperature of the heat bath, you get that the typical time to reach this threshold scales exponentially with the breather height. So again, a rare event. So let me summarize. I've given evidence of a freezing process of purely dynamical origin, which can be traced back to the existence of the adiabatic invariant Q1. Numerically, we find that tall breathers are characterized by an exponentially slow dynamics, so their relaxation times are exponentially long in their initial amplitude, and moreover, the breather relaxation occurs through rare and sudden mass exchanges, which are triggered by the creation of bound states. So this is interesting because it happens for positive temperature, where you have this Gibbsian regime. But one can imagine that the same dynamics can play a role for the negative temperature regime. And indeed, in our opinion, this is the mechanism that prevents the system to flow to the final, to the equilibrium state at negative temperature. You can have some more detailed information if you consider again stochastic models, where you now put by hand an exponentially small interaction coupling between breather and background, and in this case you would expect that your coarsening turns into logarithmic coarsening, so something that is very, very slow. Okay. Good. So I think I will stop here. I thank you very much for your attention, and if you have questions, please.
Doesn't know about the direction, or just thinks the space can be, it doesn't depend on